Hi all, this third and last lesson of Unit 9 is about network completion, the part of the design after solving the pinch topology. First, rules about sizing heat exchangers. For that we must follow what is called the stream elimination heuristics. That has a lot to do with the minimum number of units. Remember how we calculated the minimum number of units. It is if we remove the requirements of one or both streams when made in a match, we will finish with the minimum number of units. For that to be done, the heat exchanger must be as great as possible. Remember your heat exchanger design course. If the variation along streams are large in temperature, this rule may lead to excessively large exchanger areas, and these are normally split into several shields to avoid temperature cross. But here we are dealing with hypothetical heat exchanger, not the real one. These should be designed afterwards in all detail. Besides, one heat exchanger can eliminate the requirement of the two streams. This is rare but possible. In this case, the minimum number is less than expected. As a guide for completing the network, we have another criterion, the MCP difference. This is a non-mandatory criterion that can be useful in the case of many streams at the pinch when there is little guidance for choosing what of them to match. This criterion helps selecting those matches that will not prevent other future matches in the rest of the problem. In few words, it says, if you use too much MCP difference now, in the future you will find short of it for some match. Let's define a couple of concepts, individual and global MCP differences. Individual is the MCP of the outgoing leaving the pinch minus the MCP of the incoming stream, those arriving to the pinch. This must always be greater than zero. And the global is the summation of all outgoing minus all incoming. And there is one for each semi-problem. The rule says that every pinch match that you propose must have a smaller or equal individual MCP difference than the global MCP difference. Because if not, some of the remnant matches will have not enough available global MCP difference left. Gonna see with a very simple example, but remember that this has only reason when the number of streams is big. This call-side pinch topology is solved with two heat exchangers with an individual difference 4 minus 3, 1, 6 minus 5, 1 of 1 in both cases, while the global MCP difference is 10 minus 8, 2. Both heat exchangers have a smaller individual MCP difference. In the other example, this match is legal in a cold site, but it takes too much individual MCP difference 3, that is greater than 2, the global MCP difference. And then the other match that rests to complete the pinch topology is not feasible because 4 is smaller than 5. There is not enough global MCP difference left. Finally, in big networks, the remnant problem algorithm can be useful. This is simply explained. We propose a new heat exchanger with its duty. Then calculate the problem table algorithm for the rest of the network. If the utility increases compared with prior one, then this match is feasible, but some in the future will be not. If this increase is acceptable, then we continue with this match, and if not, we try with a new heat exchanger or a different duty. This algorithm can be useful in complex, heavily populated networks. And this is all for the lesson and for the unit on minimum network design.